Okay, so the conical pendulum has a support. Now, the long thread L, or the vertical, or what we also call as the equilibrium position. Now, the thread is tilted at an angle theta, and then whirled. So this becomes the mass. Its weight acts in this direction, mg. This is the angle of tilt theta. The mass is also here. Now, the shape cuts during the oscillation, its shape cuts or motion cuts the shape of a cone. The base, the object actually describes a circular motion, and the string cuts the shape of a cone, and it is for that reason that it is called conical pendulum. Conical pendulum. This is a string. There is tension in it, so let T represent the tension within the string. If we extend this weight vector here in the opposite direction, we have this angle also alternating with this angle. So if the angle is theta, we also have this as theta. So we have the tension here acting at an angle. And as usual in physics, whenever a vector component tilts at an angle, we resolve it to its horizontal and then vertical component. So this component, the horizontal component, this will be T cos theta. The vertical component, which ideally must be here, will not be placed here, but we'll place it because of equal vectors. We would act on the mass, and then this is its direction. So the T sine theta component of the tension will rather be here. Okay. So if we look at vertical equilibrium of forces, we have the T cos theta component balanced by the weight of the bulb mg. We also have the T sine theta component being unbalanced, but due to its direction, we equate it to the centripetal force, which keeps the bulb in circular motion. So this is mv squared over r. And when we divide 2 by 3, we have T sine theta over T cos theta, also giving us mv squared over mgr. We'll have the same equation as when a road is bent or when a cyclist makes that bend. So tan theta is equal to v squared over rg. V squared is equal to rg tan theta, and v becomes the maximum velocity of a conical pendulum. Okay. So once we are okay with the banking of road and its equation for maximum velocity, we must also be okay with the conical pendulum. That is why I saw the need to quickly chip that in so that we kill this stone as well with that same, that's true. We kill this bird with that same stone. Class, are we okay? Are we okay?
Yes, please.
So this becomes the maximum velocity for a conical pendulum. And it also depends on the radius of the base, the circle, which is this. This is R. And also depends on the angle of tilt theta. Ayo, something.
Please, you forgot the roots over the RJ tan theta.
Oh, thank you. So this is V max is equal to square root of RG tan of theta. Another thing you must observe is that this is also, this is the radius, and then this is the length of the string. The same angle can be taken here or to this side. Okay. So when we take the sine of the angle, sine theta is equal to R over L. Therefore, R, which is the radius, can be equal to the length of the string times the sine of the angle of tilt, theta. This is also another powerful equation you must understand under conical pendulum. Sometimes you'll be given the length of the string, but you need radius to calculate for velocity in this equation. And you need to pick the inspiration from this sub-equation. Okay. Another area under the same concept is the period of oscillation of a conical pendulum. Period of oscillation of a conical pendulum. The square of velocity from linear motion, we've seen that V is equal to omega R. So if we take omega squared, when we substitute, we have omega squared R squared. When we substitute this for V, this is equal to RG times tan theta. Omega squared will be equal to, when we divide through by G, we have J tan theta over R. What is tan theta? Tan theta is the same as sine theta over cos theta. This times R. We earlier also had R to be equal to, so we have G sine theta over R is this, L sine theta. So L sine theta times cos theta. We are breaking it down. Sine will cancel out. So we have omega squared being equal to J over L cos theta. Omega therefore is equal to the square root of J over L cos theta. We are looking for the period. Omega is 2 pi over the period equal to square root of J over L cos theta. Please help me make T the subject. Capital T would be equal to, so do that for me quickly. Help me make the period of oscillation, capital T, the subject.
Please, 2 pi over J, no, over square root of J over L cos theta.
Hey, sorry. Sorry, there's something wrong. Look through it again. Yes. Oh, I take the reciprocal of the left-hand side, do same for the right-hand side. So when you do that, you have T over 2 pi. Mamiya.
I got 2 pi square L cos theta over J. Square root of 2 pi square L cos theta over J.
No. Mamiya, we've gotten to this stage. What I have here, if I reciprocate both sides of the equation, I'll have T over 2 pi, and the right-hand side would also be square root of L cos theta over J, isn't it? If I take the reciprocal of what I have here, isn't it? Class, are you okay with what I've done?
Yes, sir.
So if I make T the subject, I'll just multiply through by 2 pi or cross multiply so that the period becomes 2 pi times L cos theta over J. Okay. Are we okay? Mami, are you okay?
Yes, please.
So all that you need to do is that you know velocity or speed is angular velocity times radius. So substitute that in place of this V equation. And then use your knowledge of tangent, which is equal to sine over cos. Substitute this and then don't forget, period is within omega. So once you substitute V for this, you can play around it and then get this. So this is the period of oscillation of a conical pendulum. Okay. Today we derived equations. Tomorrow I'll bring sample questions so we apply all that we've studied in solving it. And because frequency period is equal to 1 over frequency, we can also say that 1 over the frequency is equal to 2 pi times root of L cos theta over over J. With this, when a conical pendulum is in motion, let me go back to conical pendulum again. When a conical pendulum is in motion, the period is the time taken to make one complete revolution. Okay, so if you are asked to calculate the time taken by the bulb to make one complete revolution, that cycle, you can use that formula to calculate. The frequency F is the number of complete revolutions made within a given time. So at a time of so and so, calculate the frequency, or within 1 second, calculate the frequency. So those relations we have, or equations we have derived, would help us in determining these important quantities, okay, of the conical pendulum. So it's a very important equations, and we'll see how that is applied in solving problems tomorrow. Please, if there is any question, quickly ask. If there is any question. If there is no question, then today has been so much tiresome because of the lots of equations we have derived. So I'll spare you the remaining how many minutes? 4 minutes to relax as you prepare for another lesson. We'll continue our meeting tomorrow. May the good Lord be with you, and bye-bye.
Bye.
It's been a marathon.
Yes.
I really want us to finish this and then start with simple harmonic motion. That's why. Okay. So bye-bye.